Hey guys, welcome to the walkthrough video of week 10 problem 2.3. Jensen's for special polynomials. So this question is especially hard, especially part B, so be prepared to go through this question. Jensen's inequality says that for any convex function f of e of x is smaller than or equal to expectation of f of x. You don't need to know this for CSMT. In this problem, we will prove the Jensen's inequality holds for a subclass of convex functions called special polynomials. This is a made-up name. We define a special polynomials as the functions that can be written as this part. So this is just like a specific polynomial. Okay, so this question is actually step by step. By each part, we will prove we will prove an argument that is necessary to prove the whole argument, and then we will prove the Jensen's inequality for special polynomials. Let's start with part A. Prove that expectation of x squared is equals to greater than or equal to the expectation of x squared. Okay. A hint is to use the definition of variance. So let's just use the hint and write down the variance. The variance of x is equals to the expectation of x squared minus expectation of x n squared, right? And we know the variance is greater than or equal to 0. So this one is quite intuitive. It just gives us a of x squared is greater than or equal to x of x squared. This is bottom up. So we prove part A. And then part B. Use part A to prove e of x to the 2k is greater than e of x and the expectation to the 2 of k, for k is a natural number. So for this question, this one is really hard. It takes me a long time to think of a clean proof to it. But to start with, we want to prove a general argument of k is natural number, right? So what is an approach that you may think of if you want to prove a general statement of the k? One thing you may notice is like in the really early of the semester, we learned mathematical induction, right? Whenever you want to prove like a k is a natural number, you can start from k equals 0 or k equals 1 and use the inductive step to finally prove the whole argument. So this is kind of a hint. So let's first try to start from here, whether we can prove it through the induction. So what should be the base case? Because in the question, it tells you to use part A. So we want to use part A. And in part A is k equals 1, right? And you can see that the case of k equals 1 is already proved in part A. So we are done with the base case. So starting from here, you may feel more confident about the mathematical induction because the base case is already proved. And the second one is to go through the inductive step. Okay, so what should be the step? Oh, sorry. We first need inductive hypothesis, right? So the inductive hypothesis is k equals n the statement holds for k minus 1, meaning that e of x to the 2 of k minus 1 is greater than or equal to e of x 2 to the k minus 1. So this is the inductive hypothesis. And then finally, we can go to the inductive step. So for the inductive step, we start from the hypothesis, right? So we assume the statement holds for the hypothesis. And then we try to find a connection between the hypothesis and our, we want to find a connection between the hypothesis and the argument we want. So let's first write down the argument we want. This is what we want, right? This is what we want. So E of x to the 2k. So how do you change this 2k? How do you change this k to be k minus 1? The idea is just to take out the squared, right? If you just take out the squared, then this will be k minus 1. Right, so if you take the inner part and squared it, then it just becomes this one. So because you want to find a connection, and this is a connection you want. Then the next step is the really tricky part. How do you change this one to make it look like this one? In other words, how do you take out the square, right? So right now the square is inside the expectation. And there is no good tool to deal with it. But if the square is outside of the expectation, then we can use the hypothesis to try to solve it, right? So the only question is how to take out the square. Then let's go back to part A. You may realize that part A is exactly how to take out the square from an expectation. In part A, it tells us e of x squared is greater than or equal to e of x, and this is squared. This holds for all of the x. And x is not just like a fixed s. It's just a notation for random variable. So this x could be like x squared, and it could also be x to the 2 to the k of minus 1. So we just like this thing to be x. And apply part A. And use the statement from part A, we can take a square out of the expectation. So we right now have e of x to the 2 to the k minus 1 and squared, right? So finally, we can use the hypothesis. Let's apply the hypothesis. This function is greater than or equal to e of x to the 2 to the k minus 1, this thing squared. As we learned in high school, so you can like, maybe not in high school, but you can just manipulate the symbols. This thing squared is equals to the e of x to the 2 to the k, right? Because 2 to the k minus 1 squared, it's just 2 to the k. And this is what we want, right? So finally, after going through all of the hard steps, we get what we want. And we are done with induction because we start from the base case. We assume the hypothesis is true and we prove that this inductive step is true. So we are done with the proof. But this is not the end of the question because we still have part C. Part C, use part B and properties of expectation to prove that e of f of x is greater than or equal to f of e of x. So this is a final statement of Jensen's inequality. So let's remind ourselves what is f of x. F of x is a special case of the polynomials. So we can just write down the expression of f of x. So e of f of x should equals to e of an x to the 2 to the n minus 1 plus an minus 1 x to the 2n minus 2 plus blah, 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 all the way to a1x. So for this one, we're just explicitly writing what is f of x. Due to the linearity of expectation, we can separate each expectation. And then for each of the, and also because of the linearity, we and each an, it is so an is fixed, right? So an is not a random variable, so we can and they are the constant, so we can just take out this an. This is also because of the linearity. And this term, it looks familiar to you because this is exactly what we get from part B, right? This part. So if you look at part B, what it tells us is that so for part A, you can take out the squared from expectation. From part B, not only you can take out the squared, but you can take out the 2 to the k out from the expectation. So for this part, we apply the result we get from part B. So we have this inequality. And you may notice that this is also the expression of this special polynomial, right? Check an times x to the 2 to the n minus 1. An times e of x to the 2 to the n minus 1. So this one is exactly the same as the special, so-called special polynomial, but right now we're dealing with e of x instead of s. So this is equals to f of e of x. And finally, that is the proof of the whole question, and we are done.